All right, the induction machine is what we're going to try to figure out. Before I do it, I want to just circle back on our basic AC machine stuff. So this is what the machine would look like as I go around the sort of periphery of it, right? Three-phase machine. All right. So that means that my windings are 120 degrees offset from each other, right? So A, B, and C. This is a two-pole machine. What did it mean to be a two-pole machine? The field changes every 180 degrees. Basically, so when I put, again, I put these guys, I always show A and B and C being concentrated at a certain point, but I'm saying that the windings are sinusoidally distributed, meaning that the maximum amount of winding would be right here on phase A, and then it would decrease to 0 by the time I get to 90 degrees, and then increase again, but go in the opposite direction. Okay. The rotor moves at some speed, omega mt. Okay. And it starts out at time t equal to 0 at some angle. Now that angle doesn't matter so much when I'm talking about a induction machine. All right. And the stator currents are three-phase. Okay. So if I'm looking at this particular thing, I left out the field winding here for a second. So I'm not going to focus so much on the field winding, what current's in there. What I didn't bring with me, I intended to, is an actual induction machine rotor, right? I'll bring that on Monday, but if you look at an induction machine rotor, it looks very strange. Basically what it looks like, and what we call it is we call it a squirrel cage, right? Because it looks like you'd have a little squirrel running around inside of it, right? Basically what it looks like is it's a set of bars that go around in a sort of a cylindrical set of bars, and then there's sheets of iron in the middle of it. Okay. Unlike this field winding on the synchronous machine, I don't actually put any current directly into it. The name induction comes from the fact that what I do is I induce currents in those windings. Okay. All right. So that's what we're going to try to figure out here. All right. So if I say the stator currents are three-phase, the thing that I say, if I do this in terms of phasors, I'm going to hook this guy up to a grid. All right. I'm going to say that the voltages all have a magnitude V, right? So what are the angles of VA, VB, and VC? What's VA's angle usually? 0. All right. It can be anything, but I usually set it to 0. This guy is going to be minus 120. And this guy here is going to be minus 240. Okay. Now, if I'm talking about IA, IB, and IC, what would they be? Well, they'd be IA, just I guess, right? I. What's the angle of, in this case, what would the angle of IA be? Yeah, it's going to be negative phi z. Yeah, that's correct. It's going to lag it, right? This guy would be minus 120 minus phi z. And this guy here would be negative 240 minus phi z. All right, so basically there's cosine currents, and those are the phasors formed. Okay. Now, the question I want to talk about is, when we talked about the synchronous machine, the field and the rotor moved at the same speed. And at 0 torque, if the machine was making no torque, where was the field winding relative to the field? So where did the field winding sit relative to the field? So they're lined up with each other. Basically, we said that if there's no torque, then the field winding was sitting right at the spot where there was 0 phase or 0 B field, right? Because the force, right? The force on a wire, I create a magnetic field, put a wire into that magnetic field. So let's look at this basic picture, right? This is the whole Lorentz force law idea. Created a magnetic field, 2 magnets, north and south pole here. If I have a north and a south pole like that, where's the magnetic field? Yeah, it's basically going this way. Jumping across there, right? So I got a B field going that way. In this case, I got a battery here. Where's the current going to be? Which direction's positive current? be out of the plus terminal of that battery, right? So the force on this guy is I L cross B. Which direction would this thing move in this picture? That wire would jump, right? He would jump. Which would he go? Jump up or would he jump down? Jump up, right? So I cross B. So my fingers go in the direction of the current, then I curl them around in the direction of the B field, and then I point up in the direction of the force. If I force the current to go negative, the other direction, then it would go down, right? So this is the basic needs of force production. So in the synchronous machine, basically what we ended up saying is I got this B field that rotates around in a circle, right? So we ultimately determined that the B field here as a function of theta is some value times the sine of omega t plus theta. And it rotated around. So what we said is if the two things are moving in synchronism with each other, so if the rotor and the B field are moving in synchronism with each other, then this wire is sitting at a point where B is equal to 0, right? So the B field looks like this, and he basically would be sitting where the B field is always equal to 0. If this thing needed to make some torque, what do we say happened? If this thing needed to make torque, what happened to the rotor relative to the B field? It had to offset itself, right? It had to offset itself. I showed that quickly the other day. That means that during some transient period, the rotor has to accelerate a little bit. It speeds up and eventually gets back into synchronism again. And the B field and the rotor move at the exact same speed still, but the rotor sort of offsets itself a little bit. Okay. Here's the question. How do I start this machine? Okay. How do I start a machine that looks like this? So at t equal to 0, so let's just remind ourselves, I want to think about a motor operation for a second. So I basically have Newton's law that says J d omega m by dt. This is the net force, or the net torque. How do I write the mechanical torque and the electrical torque if I'm talking about this thing as a motor? Yeah, TE minus TM. Basically, it's an electrical torque, a torque of electrical origin coming from the currents is making the thing accelerate. And a mechanical torque of some kind is making it slow down. All right. If I'm talking about a motor, then the torque that's making it slow down is something like the motor's shaft is connected to a pump, and that pump is pushing against a fluid or something like that. All right. That's the kind of thing that we're talking about when we talk about this scenario. So the electrical torque accelerates it, the mechanical torque decelerates it. Okay, now, so if I get to steady state, what is supposed to be true about these two things if I get to steady state? They get equal to each other, right? What happens at time t equal to 0? So at time t equal to 0, this motor, it's a motor, hasn't started, it's just sitting there at rest.
It's going to take electric, right?
It's going to have to take electric to accelerate, yeah. And my omega m initially at time t equal to 0 is going to be 0 because it's stopped, right? It's in a stopped position. So what has to happen somehow is TE minus TM has to be greater than 0 for the speed to go up. Okay. So we're going to need a lot of torque to get this thing moving. So the problem we had is the synchronous machine basically required that the field and the rotor move at the same speed. So let's think about this for a second. At time t equal to 0, the speed of the rotor is 0. What's the speed of the field all the time? What set the speed of the rotating field? Right, here's our relationship for that B field. What's that? The grid. The grid's 60 hertz. So I got 60 hertz field that as soon as I plug everything in, I got a 60 hertz field coming from the grid, but the rotor's sitting there not moving at all. So I don't have synchronism at all, right? So I want to understand how would it actually work in that case, right? So we're going to look at a couple of different cases here. So we know that what we're going to get is a B field that moves as a function of time. And I want to look at basically 3 different scenarios. So the first scenario I want to do, all right, is all right, this scenario right here. What I'm showing is I'm basically keeping the rotor fixed where it's at. All right, somehow that's happening. You could do that. You put a brake on the thing to keep it stopped. So it's stopped, and then I got my B field, which is moving around as a function of time. And it's got that sinusoidal variation. Now, for the moment, we're sitting in the stationary world. We're going to do something that they talk about sometimes in machines, where I talk about frames of reference. Okay, we're gonna jump from where we sit to the rotating world. So I want to sit on the rotor for a second. If you were sitting on the rotor, basically looking up, you would see a B field that would be changing as a function of time. Sitting on the rotor, you see a B field changing as a function of time. That rotor coil, so it's a coil. Remember the fact that I'm showing this thing where it's got a circle, that means I got a field, a winding coming out, and where I have an X, it's going in, right? So based on the way this guy is set up right now, somehow that rotor is not moving. So this is what would happen at t equal to 0. What would be happening on the rotor coil? If it was just sitting there like this, what would be happening on the rotor coil? You would induce a voltage, right? Why would you induce a voltage? Faraday's law. Basically, what I have sitting there is I got a coil, and I have a changing magnetic field passing through that coil. So right now, it's just a function of time. If you were sitting there on the plane of that coil on the rotor, you have a changing B field passing through there, right? If I wanted to figure that out, this is a B field. I can relate that to a flux, right? Because phi equals B dot dA. We can figure out all that stuff. But there's a changing magnetic field going through that thing, right? And we know that, if I jump down here, the B field passing through that thing, this is the way we write it. And I included the phi z in this thing. But this is the way we write that field. So there's going to be a voltage induced, which is related to d lambda by dt, right? And that d lambda somehow is n times the area times dB by dt, right? And the B, in this case, that's passing through it, is equal to this guy. All right, so let's just call it a constant times the sine of omega t minus theta. And I could put the power factor angle in there if I wanted to. All right. So what would be the frequency in the case that I showed here in this particular image? What is the frequency of the voltage here that would be induced in that thing? Yeah, it would be the same as the grid frequency, right? It'd be the exact same as the grid frequency, because there's essentially a changing 60 hertz field that's passing through this thing. All right, now this is what happens when I'm at 0 speed. All right, so at 0 speed, what's going to happen is you're going to induce a current into the rotor. All right, and the way the induction machine works is it just has a set of short-circuited coils on it. Right, so there's just a coil that's short-circuited sitting there on the rotor. So I'm not putting a current into it, it's just short-circuited. And so sitting there like it is right now, if there's a B field passing through that coil, that B field induces a current in the wire. And then what's going to happen to that wire? It's going to start to move, right? So I induced a current in the wire, and the B field's going to interact with it to cause it to move, right, via the force law. All right, so now this thing's going to start to accelerate. Now, eventually, if there's no load on the machine, and I don't want to get into all those details just yet, but somehow let's assume it gets up to full speed. All right, what would full speed be? What's the fastest this thing is going to move if I hook it up to the grid? Basically 60 hertz, right? It can't move any faster than the field does. All right, turns out it can in a generator scenario, but as a motor, it can't do that. Okay.
So does the mechanical speed still depend on the number of poles then?
The mechanical speed still depends on the number. So in other words, it can only move as fast as the rotor. The rotor can only move as fast as it relates to the field, right? So if the rotor is moving at 1800 RPM because it's a 4-pole machine, the field still ends up moving at 60 hertz, right? But for a 4-pole machine, the fastest it can move mechanically is going to be half of the grid speed. If it's a 6-pole machine, it can only move at 1/3. If it's a 8-pole machine, it can only move at 1/4. If it's, and so on and so forth, right? But yeah, basically the relationship that happens is essentially that the fields, and you guys don't even get too lost in this, but basically if I have a 4-pole machine, the fields are still moving at 60 hertz, right? If I have a 6-pole machine, the fields are still moving at 60 hertz, right? That's the relationship that's always going to exist, which we want to touch on here a little bit more. All right, if this guy gets to full speed, what's true about the rotor and the field? They're in synchronism with each other. All right, so I think that is my, let me see. I think that's this one. Yikes. What was that? That's this one. All right. Here they are moving in synchronism with each other. Now, put yourself on the rotor. You were sitting on the rotor, moving with that thing. Is there a changing B field passing through that coil now? No. Right? Based on that, there's no current induced in the rotor. So is there any torque? No. Right? No torque on this thing. So basically what we've kind of established is at 0 speed, there is a current induced in the rotor, and there will be, so there's a changing B field going through it, there's a current in the rotor, there'll be a torque. If I get to full speed, right? So basically at full speed, so I took screenshots of it, but let's just go back to look at the picture again, right? At full speed, from the perspective of the rotor, there is no changing magnetic field passing through this thing. So there will be no current and there will be no torque. So at full speed, and we're going to give full speed a name in a second, but at full speed, the voltage induced d lambda by dt is basically equal to 0 because the B field from the rotor perspective is equal to 0. There is no change, or the negative dB by dt is equal to 0. From the perspective of the rotor, right? If I'm looking at this guy, this is what's tricky about it. Looking at that picture that you see right there, sure, the B field's changing as a function of time in the stationary world that we're sitting in. But if I were to sit on the rotor, from the perspective of the rotor, there is no changing magnetic field passing through the rotor because they're moving together with each other. So there's no current induced. There will be no force on that thing. So at full speed, the electrical torque is going to be equal to 0. At 0 speed, there will be some electrical torque. It will be definitely greater than 0. I don't know what it is just yet, but I know it's going to be greater than 0. Now the question would happen is, let's say I got this thing up to full speed. Okay. So let's say I get to my full speed scenario.
Let's do this all with a synchronous motor.
This is with an induction motor. Right? So yeah, let's make sure we're clear on that. With the induction motor, what I'm saying is it's the same basic type of machine, except what I'm doing is I'm not putting a current into the field coil. I'm letting it appear there magically on its own. All right. So at 0 speed, current gets induced. Full speed, there's no current there. So if I go back to my Newton's law relationship here for a second. All right, let's write out the Newton's law relationship. So I have J d omega m by dt equals tau electrical minus tau m. And so let's look at this for a second. So if I have case one. Let's look at a couple different cases. Case one, let's say omega m is equal to 0. What we said is we induce a current in rotor. And there will be a B field passing through that thing. And so the torque electrical is going to be greater than 0. Don't know what it is, but there's definitely going to be a torque. This guy's going to move. Case two that we just looked at was what happens if omega m is equal to, the maximum. And I'm going to say for now that I'm going to do this for a two-pole motor so that we don't get too lost. All right, for a two-pole motor, omega m and omega are equal to each other. This is full speed. So this is no current induced in rotor. And the speed is, or the torque is equal to 0 because there's no current, right? That I cross B can't exist, okay? So what's the mechanical load if I get to this condition? So these are both steady state things. So at omega m equal to 0, there's a torque on this thing. There's a current induced. At full speed, the torque is equal to 0 electrically. So what's the mechanical torque? Mechanical also has to be 0. This guy's inducing no torque. He's not doing anything. He's at full speed, just running around, rotating, doing nothing. All right. Now, what happens if I try to load the motor down? So how would I do that? So this guy gets up to full speed. Let's say I just grab the shaft in the machine, right? And I'm comfortable. If it's a 1 horsepower machine, something like that, I'm comfortable. I'll grab the shaft. And if I grab the shaft, what's going to happen? Well, mechanical torque goes up, right? And it's going to be a little bit bigger than 0. That means that, well, yeah, so for at least a short period of time, what's going to happen is electrical torque minus mechanical torque is going to be negative. What's the speed going to do? Slow down. All right, so the first thing that's going to happen is the speed's going to slow down. Now the rotor and the field aren't moving at the same speed anymore. All right, so let's look at that scenario. And yeah, eventually the electrical torque is going to increase, but what's the mechanism by which it happens? So let's try that situation. He's going to slow down a little bit. So this is why. So he was basically, what was going on is they were both moving at the same speed. I grabbed the shaft. He's going to slow down. All right. So let's look at what's going to happen on the rotor in that scenario. All right. So here's the case. Watch carefully what's going on. What do you notice about the B field and the rotor?
They're starting not to be constant with respect to this.
Starting not to be constant with respect to each other, right? Basically, it's moving a little bit slower. In this case, this is pretty different. They're moving, one's moving at half the speed of the other, right? If I was sitting on the rotor, there's going to be a current induced in the rotor, right?
No.
Yeah. What would the frequency of that current be? It'd be about half, right? It's moving at half the speed. It's going to be half the frequency of the current. So if I talk about what happens in that particular case, all right, if I'm in this other condition, V equals d lambda by dt is NA times dB by dt. The B field that I get is going to be somehow, so the B field on the the rotor, from the perspective of the rotor, is going to look like BA or some value, some constant. And the frequency of it's going to be omega minus omega m t. All right. Something like that. So from the perspective of the rotor, right? This is the sort of the key perspective, right? When omega and omega m are the same, basically I'm inducing nothing. When omega and omega m are completely different, right? In other words, one's 0 and one's at full value, I get 60 hertz going through there. If I grab the shaft, it slows down a little bit, and the frequency that I get in there is basically going to be omega minus omega m. So it's going to be a little bit of current going through there, and that current has a very, very low frequency. How much torque am I going to get in that case? Or will I get torque in that case? What causes the torque? Right? Well, so in this case, because they're moving at different speeds, there is a changing magnetic field passing through that thing. That means there is a current induced. And what's going to happen? There's going to be a torque on that thing, right? Because basically what makes there be a torque is basically that the current on the rotor is sitting in a magnetic field, right? There's an arrow of magnetic field strength at that point. So there's going to be a force on it. All right. What that leads to is basically this behavior ultimately. All right. What the torque looks like as a function of speed looks something like this. Now, this particular image here is an image we call the torque speed curve of the motor. All right. And let's see if we can make sense of it here. So at full speed, and I did this for a 4-pole machine. All right. So that's why the maximum speed here is 1800 RPM. So at 1800 RPM, what's the torque that the machine produces? No, 0, right? At synchronous speed, this guy produces 0 torque. At 0 speed, I just used the term, I said, so full speed, I sometimes call synchronous speed because that is the point at which the field and the machine are moving at the same speed. They're moving in synchronism with each other, right? So full speed is sometimes called synchronous speed. At 0 speed, there is also some torque production, right? Because there is a current induced. And then at some point, at some particular speed, it maximizes, right? And it's not particularly special where it maximizes, it just maximizes, right? There are different types of induction machines that are designed in different ways to get this torque speed curve. But basically what it tells us is as the function of the machine speed, this is how much torque it makes. Okay. And effectively, if I look at the rating of a machine, machines are typically rated to operate in a range like that. And one of the things that you guys have maybe noticed in the past, a couple of times I've shown nameplates on motors, right? So if we look at a typical motor nameplate, and I didn't put one in here, but I'll weigh down my computer and and have it give me an induction motor nameplate. What I typically show you on those nameplates is that the speed is not, it gives you a rated speed. And I said that rated speed is usually a little bit less than the speed you would expect. So if I look at an example here. All right, this is not a good one to choose. Let's choose you. All right. So if you guys, I don't know why you can see that there since it's black like that. You guys can see that it says the RPM is 1770 RPM. How many poles do you think this thing is? 4. And the speed is a little bit less. That's the rated speed on this thing. What this nameplate means, this is a 10 horsepower motor. What it means is that it's producing 10 horsepower of power mechanically at 1770 RPM. Now, let's see if we can make sense of what's going on, right? Because we basically laid it out right there. And we can look at our different cases here for a second. So at 0 speed, there's a torque. It accelerates this guy. He gets all the way out to full speed. At that point, no torque. If I then load it down, right, I grab it, we said what happens initially is when I grab the shaft, the mechanical torque is going to be a little bit bigger than the electrical torque at that point, right? And so what we said was, in that scenario, where did I put it? In that scenario, we said J d omega m by dt is equal to torque electrical minus torque mechanical. If I grab the shaft, I was at synchronous speed, this guy goes negative, he's going to slow down. Once he slows down, it starts to induce a current in the rotor. Now there's going to be torque made again, right? And so what happens is the machine slows down and finally reaches a point where it's producing just enough torque to balance the mechanical torque. So if I grab the shaft and I put, let's say I put 5 Newton meters of torque. when I grab the shaft. So here's 5. The machine will slow itself down so that it's producing exactly 5 Newton meters of torque to oppose it. Okay. So when a machine like the one I just showed you said, okay, it's 10 horsepower, 1770 RPM, what that means is that when the machine's producing 10 horsepower, it's moving at 1770 RPM. He slows down just a little bit. So this looks a little bit weird. You look at this curve and you say to yourself, well, wow, I got lots of speeds I can work with here, right? But the reality is we only work with a pretty narrow range. All right, so in that example I pulled up, he only slows down 30 RPM at full power. All right, or at rated power. So that's the basic concept of operation of an induction machine, right? Is to say that I induce a current in the rotor. At 0 speed, he's sitting there stationary, so I induce a 60 hertz current in there. At full speed, I don't induce any current in there. And then if I slow it down, then the rotor is moving a little bit slower, and I'm inducing a current that has a frequency omega minus omega m. Yeah.
How can we operate it at the maximum torque?
That would be a very dangerous thing to do. Because the issue that you run into is, and it's a little tough to go through all those details, but if I try to operate up here, that's kind of an unstable condition, because if there's any slight variation in the load,
Yeah.
I may not be able to make that. All right, without getting into the weeds on that, basically the machines are always designed to operate somewhere over in this range, a very narrow range around full speed.
So the induction machine can't run if it's not loaded.
It can run unloaded. Yeah, if it gets unloaded, it just goes out to
So it just
here.
depends on it.
Yep, it just spins around. Basically, if I look at an induction machine, how much power is going into an induction machine if it's not connected to a load? 0. That sounds weird to people at first. You're like, wait a minute, it's spinning. If it's spinning, why? If it's spinning at a constant speed, I'm not having to do any work to keep it there. Now, you know for a fact that I'm wrong when I say that, because there's got to be friction. So in reality, nothing's going to spin at 1800, but it might spin at 1799 or 1792 or something, or it's going to spin at a speed really, really, really close to 1800, where there's just enough torque going into it to fight off the friction of the air of it as it spins. All right, but he operates. Sometimes people call induction machines constant speed machines, because for the most part their speed doesn't change that much.
So it'll still operate unloaded, but it won't make any power unloaded.
It'll still operate, yeah. And those synchronous machines, I said the synchronous machine was going to be tricky to start, because for the synchronous machine to make torque, what did it have to do? Well, the rotor and the field needed to change at the same speed to make a constant torque. So if you look at the way an induction motor or a synchronous motor works, is you short circuit the field winding at t equal to 0, don't put any current into it, so that it operates like an induction motor. You get it up to full speed, then you unshort it, and then you put in the current that you want. That's how a synchronous machine works. All right. Is it starts like an induction motor, and then you switch it over to a synchronous motor. All right. So this is the induction motor is basically, when we talk about how long an induction motor lasts, forever, right? Why forever? Because the thing that wears out on any motor basically is the bearings wear out, right? So bearings can wear out. On a synchronous machine, I have to somehow get a current into a rotating piece. That's not easy, right? I have to somehow have something called a slip ring that forces it in there. And that means I have two rotating, one stationary and one rotating device that are touching each other. That's going to wear out after a while. The beauty of the induction machine is there's no touching, right? I'm just inducing the current in that thing. So these things last for decades and decades, all right, without really ever wearing out. And they operate in a very narrow range. All right, that's the basic principle by which these things work. All right, now I want to figure out, a little bit more of the circuit model. To be able to analyze how they operate, we need to understand sort of the circuit model a little bit. Now, I said these things are like constant speed machines. They don't change their speed much. we're going to talk a little bit about, in the modern context, I operate these things very often with what I call a variable frequency drive, or a VFD. And if that's the case, then what I need to do is I need to connect the motor to something other than a 60 hertz source. All right, and we're going to talk a little bit about how we control those things. Okay, because nowadays there aren't too many motors that just run off the 60 hertz grid. There's usually some electronics between the motor and the grid. All right, and so we'll talk a little bit about that. And we'll go through some specific examples that I've got for that too. Questions about the basic operation of this thing? It's fairly straightforward in concept what it's doing, and the name says it all. You're inducing the current. There's different torques based on it.
So the hardware, I guess, or the physical machine itself is pretty much the exact same.
The physical machine is almost the exact same as the synchronous machine. Yeah. The one difference about it is that if I look at the machine, there is a three-phase set of windings on the stator and on the rotor. I don't have to have a three-phase set of windings on the rotor, but I do. Okay. All right, so there's a three-phase set of windings on both. The thing is that AR, BR, and CR are short-circuited. They don't have to be. I can actually connect to them if I want to. And in some wind turbines, that's a common thing to do. Okay. But most induction motors that exist in the world, there's just short circuits on those rotors. Okay. And I'm hooking up AS, BS, and CS to the grid. Okay. All right. I want to define something real quick though for a second before I get too far, which is to say the frequency on the stator is omega, which is 2 pi 60. The rotor mechanical frequency is omega m. All right. If I have a two-pole machine, right, then this will also be 2 pi 60. Okay. Let's just keep it as a two-pole machine, and I'm going to generalize it for a second. So that will be, or at least let me be careful about that. All right. At full speed, it'll be 2 pi 60. Let's just call it omega m for a second. Okay. What's the frequency of the current that got induced in the rotor? So the current induced in the rotor. So basically, if the machine was stationary, if the machine is stationary, what's omega m? If it's not rotating, what would the mechanical speed be? 0. And what was the frequency of the current that was induced? 60 hertz. Yeah, 2 pi 60. If they were rotating at the same speed, we said there was 0 current, or a DC current, I guess, a 0 current. So basically, at full speed, it's a 60 hertz current. 0 speed, constant frequency. And if it was a little bit less than full speed, we said it was omega minus omega m. So the current in the rotor is basically omega minus omega m is what its current is. Now, I wrote this out here for a two-pole machine. This would be two-pole. All right. What would it be if I had a p-pole? The stator frequency is still what? Still omega 2 pi 60. What's the frequency that I get here? So p over 2 times omega m. And the current in the rotor would be omega minus p over 2 omega m, like that. So sometimes what I define is a quantity called slip. All right, so I say that the machine has a slip S. And S is defined as basically omega minus p over 2 omega m over omega. Okay, where I'm going to give omega a name, which I've already kind of given it. Omega is what I call the synchronous speed. If the motor is operating at full speed, what is S equal to? 0. No slip is what that means. If the motor is stopped, if it's stalled, and omega m is equal to 0, what's the slip? Omega m is equal to 0, what would S be? 1, right? So basically, we sometimes write this and say, here's the speed, like this, but oftentimes what they also do is they say the slip goes from 1 to 0. So there's no slip at full speed. Slip in the context of the fact that the rotor, once I loaded it down, was starting to slip. It was starting to move slower than what the field was. So it's slipping behind it, right? So at full speed, synchronous speed, the slip is 0. Right, so they define this term, and that term becomes particularly useful as I kind of work through the circuit model. All right, and that's, this is one of those things that on the FE exam on motors, they always ask you that kind of stuff, right? What's the slip? They'll give you stuff like the speeds and the number of poles, and that's a common sort of question for them to ask. Okay, all right, so I've defined that term, which becomes really useful to us in a little bit. All right. And I'm going to define this guy a little bit too. I'm going to add one more definition to say that this current in the rotor, its frequency is omega r, right? So omega r is omega minus p over 2 times omega m, right? That's the current, the frequency of the current in the rotor. And that, again, that definition will be useful to us here in a little bit. Okay. All right, now I want to figure out a circuit model for this thing, which is going to be a bear. So when I want to figure out electrical circuits, we've done this with transformers and everything else, right? With the synchronous motor. How did we do that with the synchronous motor? How did I build an electrical circuit model for this thing? What was the process for building an electrical circuit model for the synchronous motor? Find all the flux linkages. And then once you know the flux linkages, you take the derivative, right? You take Faraday's law to get the voltages. Now, if I looked at phase A, I looked at lambda AS. How many terms does lambda AS have? Yeah, it's got how many total? A lot is basically going to be how many? 6, right? There's going to be 6. There's going to be LAS, IAS, plus there's going to be LAB. So there's a mutual flux from coil B on the stator to coil A on the rotor. And there's going to be another one from C. And then there's going to be some rotor dependent ones, 3 rotor dependent ones that come in, right? It's going to be ugly. So 5 mutual terms and 1 self term. And it ends up, I can write it all out. You write it out in matrix form. I have a 36 entry, 6x6 matrix. Ugly, very ugly. Okay, nobody uses it. Well, that's not true. It is needed. It's needed when you do, excuse me, some very fine position control with this thing. I need to know certain things about that guy, but I don't want to go into it. It's a lot of math. It's ugly. Intuitively, we can kind of figure out what the model is going to be. All right. I'm inducing a current on the rotor. So what is this thing kind of like? If I'm inducing a current on the rotor, where have we seen that before, where I induce a current somewhere? Back in the first half of the semester, where did we induce currents? Transformer. This guy's like a rotating transformer, right? I am inducing a current on the other side of this thing. So I want to intuitively kind of figure out what the circuit's going to be, right? So if I look at phase A, let's remind ourselves, what's the transformer model look like? If I'm looking into the terminals of a transformer, what do I have in the terminals of a transformer?
It's inductor.
No capacitors, yeah.
Induction.
All right. Well, that was one way of looking at it. We had two different ways. There could be a dependent voltage source of some kind. And then we learned it just in terms of magnetizing inductances and stuff like that. So if I'm looking into a transformer, there is a resistance, right? What else? So there's an inductor that's going to be here, and there's an inductor that's going to be here. Okay. So I'm looking at phase A, and I can include things like the resistance of the core losses and stuff like that. But what are these things modeling if I'm looking at sort of a single winding on a transformer? Well, the effect of the changing flux over time, right? So, but these two L's and this R, what do they model? What physical phenomenon? This guy I'm going to give a name RS. What is that resistance model? Does she say the source? It could be. But I'm just saying, looking right at into the transformer windings, that would basically be the winding resistance. In other words, just the copper losses. What are these two inductors here? There were two inductors in our model.
Mutual inductance. One's magnetizing.
One's magnetizing. Yeah, this is my L mag. Right? Now in the synchronous machine, I didn't talk about the other one, although there is another one. Right? What other inductance, if I talked about just a transformer, what's the other inductance that I have in a transformer? I have the magnetizing. What else did I have? There was another term, and that was the one that turned out to matter a lot when we did, like, when I had you guys doing power systems problems. That one mattered a lot. What's the other term? What's this L? It's the leakage inductance, right? What I said was if I had a transformer, a real transformer, right? There would be a set of windings. Most of the flux is going to stay in the core, but what's true about some of the flux? Some of it leaks out, right? There's some flux that sort of escapes out of the core. This guy here is what I'll call LS leak. And this guy here is the magnetizing inductance. Okay. That is effectively what happens inside of a real transformer, right? Now, this guy acts like a transformer, right? So if you're going to act like a transformer, there better be an ideal transformer over here. Again,
phase A of the induction.
Yeah, and I'm not because he acts like a transformer, and I could go through all the details of how that sort of works itself out, right? But let's ask ourselves for a second. This guy's going to be the number of turns on the stator, the number of turns on the rotor. What's going to be on the other side of this thing? What was on the other side of a transformer model?
It was just
it's the other leakage. It's the other resistance, yeah. All right, and then this over here, this would be VAS. This ends up being one of the phases on the rotor. Now there's a problem here for me. This is a complicated Yahoo type of problem here for a second, right? Because what's the frequency of this voltage right here? This guy is 60 hertz. Omega is 2 pi 60. On the rotor side, what was it? It was different. The rotor was different, right? The rotor we said was omega R, which is omega minus P over 2 omega M. It's different, right? If I have two different frequencies in my circuit, doesn't that make impedance analysis kind of difficult? It does. I gotta weigh out. All right. So basically, the issue I have here is this. But this is our basic model. And you should be able to buy that that's the basic model. If I went through the analysis really, really carefully, what I would see is that VAS ends up being whatever that resistance is times IAS, right? That's the current, if I define it, right? This is the current here. And IAR would be the current here, right? It ends up being VAS equals R times I plus J omega times whatever the leak is plus whatever the magnetizing is times IAS plus some J omega times whatever is reflected from the secondary. All right. So there's some reflection factor. All right. I don't want to, yeah, it's rated the turns ratio squared or whatever, right? What about for the rotor side? It would be whatever the rotor resistance is times IAR. But instead of on all the rotor stuff, what would be the frequency of all the rotor stuff? Be J, yeah, omega R times, let's say, some factor times all the rotor stuff, right? And I don't want to focus on all that because we can get lost in those details pretty quickly. How can I possibly get those two things to have the same frequency? I got a problem because I got a circuit that has this, and they have two different frequencies. Well, we had a way to relate omega to omega R, didn't we? How did I do that? So omega R was omega minus P over 2 omega M. And I also defined that thing called slip, didn't I? And what was the slip? Yep, slip was omega R over omega. So I can say that omega R is equal to S times omega. It's just scaled, right? So I can turn this into, instead of omega R, I can say it's S omega. And then what I do is I rewrite this as VAR over S, R over S, times IAR plus J omega times all the inductance stuff that I would have with a transformer like that. Now I have one circuit that has the same frequency throughout. But what have I introduced with this term? I've introduced a resistor that depends on the speed of the motor. All right, a resistor that depends on the speed of the motor. All right, now, the other thing, what did I say was usually true about the induction machine windings? Do I apply a voltage to the induction machine windings? No, I short circuit them. I try to induce a current in there. So usually VAR is 0 because I just make sure it's just a coil. I'm not applying a voltage to it, it's just a coil. All right, so what that means is my ultimate model looks like that. All right, my ultimate model looks like a transformer where what I have is a short circuit over here on the rotor winding, and I have the leakage from the stator, and I have the speed dependent resistance right there. All right, and let's just remember S is equal to omega minus P over 2 omega M over omega. So again, I want to kind of intuitively figure out what's going to happen inside this thing. All right, now I can also, if I want to, right, I showed this guy's R sub R, L sub R like this. What else can I do in a what do we do when we're analyzing a transformer model? What do we typically do with the stuff on the secondary? Reflect it. All right, and that would be related to the turns ratio or whatever. I could, if I wanted to, and have that sort of turns ratio effect in there, right, where I've sort of mapped that stuff over, right? But typically what I do is I don't know what that stuff is, and I usually just know what I call these things in this particular model This is what I end up with for the model where I reflect everything over. Somehow R2 and X2, those are related somehow to the turns ratio. Okay. Don't care because to be quite honest with you, I don't know what the turns ratio is in a machine. All right. But this is what it looks like. I've reflected that stuff on the rotor over into the secondary. All of those reactances are using the 2 pi 60. Okay. Let's think about this S for a second. The thing that's weird about this, all the reactances have the same frequency. The S depends on the speed. So let's see if we can make sense of what is going to happen in this particular case. We said omega minus P over 2 omega M over omega. So let's think about the two cases we said. So let's say omega M is equal to 0. And let's say omega M is, sorry, omega. So my speed is at full speed. Okay, so this is 0 speed. And this is full speed. What are my slip values at those conditions? 1 and 0. This is S equal to 1. This is S equal to 0. Okay. All right. So at S equal to 0, what? Well, R2 over S is going to be really big, right? So when S equals 0, so with S equal to 0, this would be full speed. This circuit is going to look like this. There's some resistance, there's the leakage, there's XM. So at S equal to 0, R2 over S is what? Infinite. So I have an open circuit. Okay. So basically at full speed, this is my circuit model right here. So this is my RS. This is my, I'm calling X1. This was the leakage. This was the magnetizing. How much power is this machine making at this condition? What took power? In other words, what took mechanical power? Torque. Right? How much torque did we say there had to be at full speed? None. And here you can see there's nothing happening, right? Basically what's going on is there's some current going through this machine. And what did I say this resistance represented? Heating in the coils, right? This is copper losses. So yeah, there's some power going in because there's winding heat, right? The machine's getting a little bit hot, but there's no power coming out of it. Now, what would happen if I got to the other condition where S equals 1? What happens when I get to S equal 1? So this would be 0 speed. What's the circuit do in that condition? Yeah, basically this, I get just R2, and this guy almost looks the same. This is like a short-circuited condition now, right? In this particular case, usually it's the case that the magnitude of XM is usually much, much greater than the leakage plus R2. All right, usually that's the case. So if the magnitude of XM is much, much greater than the impedance of the other branch, what does that mean? Yeah, where's most of the current going to go? Going to go through this branch, yeah, like that. And it's going to skip XM. So in this case, what would you expect the power to be? Well, these resistances are going to be small. What do we know about leakage inductance? Leakage inductance represents the flux that's leaving the core, right? So what do you think the leakage inductance is going to be? It's going to be small, right? I want the leakage inductance to be small. So in this case, the total impedance of the circuit is pretty small. So what's the current going to be? Pretty big. What's that mean? Inrush current, right? This is where my currents are fairly high in this particular case. right? So this is a scenario at zero. This is zero speed. My currents are really high. All right. That current being really high makes the machine make a lot of torque. All right. So what I want to do is I want to kind of derive the torque relationship, but this is our basic circuit model. The only thing that's weird about this circuit model is I have the speed dependent resistance. All right. So when S equals 0, he's at full speed and I have an open circuit on this guy. There's definitely a current flowing. There's very little power. The only power going in here is basically because of the heating of the machine. Most of the complex power in here is going to be reactive, right? Because X is going to be a lot bigger probably than R is. All right. So most of this complex power would be reactive. Whereas in this case here, right, I'm not sure whether it's going to be reactive or resistive, but the resistor values are very small. The current's going to be very high. Okay. I want to figure out, how do you think I figure out the torque? How do I figure out the torque in this situation? What's that? Well, I could. This one turns out to be pretty easy. Yes, I could totally do the co-energy. But you know what? No one likes that, do they? All right, so this one's a lot more fun. All right. So I'm going to call this XM, X1, X2, R1, and R2 over S. So the actual mechanical power somehow must be related to the power going into this thing. And so what I do is I define the power going across the air gap. In other words, the power crossing into the field winding, or sorry, into the windings on the coil, on the rotor. For one phase, how would I calculate? I'm going to call this current here I2. Okay. For that, how would I calculate the power going into this guy right here? So the power into the air gap is the power into that resistor. Do what? Yep, I squared R, right? So it would be, yeah, I squared, so magnitude of I squared times R2 over S. And this is for one phase. I just did this for phase A. So what should I do for the whole machine? Multiply by 3. All right. Now, this guy actually happens to represent two different things. One thing is going to be the mechanical power. The other is going to be basically just what I'm going to call the heating loss, right? There's just the fact that I have current going through a resistor means that there's an I squared R. So I can basically write this as PM minus 3 I2 squared R2, like that, right? So what I have is the 3 magnitude I2 squared times R2 over S equals that. So I can figure out what the mechanical power is. And the mechanical power ends up being 3 I2 squared times R2 times 1 minus S over S. If I solve for that thing, right? Sure, move that down, right? Yeah. Minus S over S. That's the mechanical power. How do I get from, and when I say mechanical power, I guess I want to be clear about this. This is the power that is going into mechanical work. All right, is that. How do I get that to torque? Divide by omega m, right? So I know that torque, one more blank one here. So PM is 3 I2 squared. It's 1 minus S over S times R2. Like that. All right. Now, to get to torque, the torque produced by the machine, which in steady state, torque electrical, torque mechanical are the same, right? This guy becomes is PM divided by omega m. So it becomes this 3I2 squared 1 minus S over S omega m times R2. And I can rearrange that whole thing ultimately to this 3I2 squared over S. Sorry, do it this way. Over omega times P over 2 times R2 over S. This to me says something particularly important. I can intuitively rationalize what's going on here. All right. The current is proportional to the, or the torque is proportional to the current, right? Or in this case, the current squared. That kind of makes some sense, doesn't it? Because if I'm talking about this machine being at, let's say, full speed, when it's at full speed, how much current did I have induced in the rotor? None. No torque now. Okay. It's entirely consistent with that statement. At zero speed, right? We said there's a current in there. It's going to be kind of large. All right. So I2 is kind of big. This also tells me that the torque I get is ultimately a function of the slip. And that gets me back to the picture I had right here, right? This is actually showing me 3 times P over 2 P over 2 omega times I2 squared R2 over S, right? What this is showing me is what that torque actually looks like as a function of speed. And it maximizes at some point, usually kind of close to the full speed. But we usually, like I said, we try to operate it somewhere in here. All right. So when we look at these induction machine problems, basically what we're doing is we're looking at this relationship for the torque. And we're looking at that electrical circuit model to understand the basic behavior of what's happening. But, you know, one thing that some of you guys probably heard the term inrush current before. Inrush current means there's a lot of current that in the machine when it's starting. Why? Because essentially it's like the rotor is presenting a short circuit and a lot of current is going in there. That current is producing a lot of torque to get the machine accelerated, right? And eventually it gets to full speed and blah, blah, blah. All right. Now, what that's showing is what the electrical torque looks like. If I want to figure out how this machine behaves in steady state, what do I have to do? Well, I have to superimpose across this what the mechanical torque would look like as a function of speed. And the mechanical torque as a function of speed usually looks something like this. Right? And usually the two things intersect at some point. All right, we'll talk about that a little bit on Monday. Right? But if I had something like a pump torque would usually be something like some constant times the speed squared, right? And they intersect with each other at some particular point. All right, and wherever they intersect should be close to the rated condition of the machine. And if they don't intersect at the right point, the old school thing was to put belts on there so that they basically matched at sort of the right speed that the load wanted. The new school thing to do would be to put a drive on it so that the speed matched up to right where it should be. Okay, so we're going to talk about that basic piece, but this is the basic function by which an induction machine works. All right, and we get this relationship that the current and the torque are directly related to each other. So you can see this when I'm at zero speed, there's going to be a lot of current going into that thing. That current helps it accelerate quickly. Okay. All right. So that's it.